the multidisciplinary issues to facilitate interaction between researchers, industry representative, and the academic community in the field of research and development, and also to distribute current findings of the researchers at Ibu Sina and also in UTM itself. And we have the presentation from the distinguished speakers, Dr. Sugeng, and after that we have the question and answer session, or any feedback on the ideas and suggestions from the audience is welcome. And the last of this program is a refreshment at room theatre 2. And without wasting any time, I would like to introduce the speaker, Dr. Sugeng Triwahyono, senior lecturers at Ibu Sina Institute for Fundamental Science Studies, University Technology Malaysia. The academic background is a Doctor of Philosophy, Divisions of Molecular Chemistry, Graduate School of Engineering, Hokkaido University, Japan, Masters of Engineering, Chemical and Environmental Engineering, Postgraduate School of Engineering, Kitami Institute of Technology, Japan, Bachelor of Engineering, Department of Industrial Chemistry, Faculty of Engineering, Kitami Institute of Technology, Japan. And the specialist expert in the design and synthesis of nanomaterials to develop the mixed metal oxidant. More on synthesis of zeolite materials, problem in analysis of sample, design and manufacturing of reactor, and etc. So we are welcome Dr. Sugeng Triwahyono with the title Hydrocarbon Originated Protonic Acid Site for the Seminar Series 13. You are welcome.
Thank you, Dr. Roman, for very nice introduction about me. Good afternoon and Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to the director of ISNA and the lecturers, and also our students guests from Japan, and also to students. Okay, actually, I don't remember the topic that I have to deliver today, but I just picked one of my slides. So I found this one, hydrocarbons originated protonic site. Actually, when I look at the original titles of the presentations, it's not so literally this one. This one is the basics of the what we call it my research regarding this one. Okay, actually before I have to go regarding this topics, we have our research group have a topic regarding this. I'm sorry, actually I have to read this. Okay, this one is our original idea is molecular hydrogen originated protonic site, and that's after we do some research, so we elaborate this research to hydrocarbon originated protonic acid site. Actually, the concept is quite similar, but differences is the previous one is come from hydrogen, and the other one is come from hydrocarbon. Okay, firstly I want to go to molecular hydrogen originated protonic acid site. Okay. Okay, the idea of hydrogen originated protonic site is come from usually researcher generate active sites, means protonic sites come from the structure of catalyst. Mean by modification of catalyst using, for example, ammonia, using HCl, fluorine, so we can get the solid site. We can look at here maybe from the network of silica and oxygen and silica or alumina, we can substitute silica with alumina and we can generate proton here. This is the usual concept when we want to generate acid site. But in our idea, because this one is just proton, maybe proton can be treated from other sources. I mean, not from the original catalyst. Maybe we can treat it from other sources. For example, hydrogens for an other molecule, for example, alkanes, cycloalkane, or something like that. So this is the idea. You can look at the below picture here. Hydrogen can be treated from proton or from the catalyst. This process also can be reversible. It means when we generate proton, so we can also remove proton from the surface. This is our idea, and this is just the backgrounds. Maybe this is when Cox wrote a few years ago, he wrote that often the zinc oxide can generate proton and hydride. This one can be observed using FTR, and Colusia also reported that in magnesium, in addition of hydrogen, actually this one cannot generate hydrogen. And Hydrogen our research group proposed that hydrogen can be generated maybe either on solid catalyst and also basic catalyst. Okay. From this previous literature review, so our research group raised the question: does this one is always mean hydrogen group? Does hydrogen format on solid base promote as catalyzed reaction? So after we do some research, we do some calculations. So the answer is no. Proton cannot be generated over the base catalyst, but it can be generated over the solid catalyst. Okay, I think it will be more clear after go possible slides. Okay, this one actually we focus on the one of the good catalyst mean in the term of acidity, in the term of structural material. Usually we use sulfated zirconia. The sulfated zirconia is one of the strong oxide which can be used to isomerize, for example, butane, also alkane, also pentane. I mean, for general alkane, you can use this one at room temperature. It means it's quite difficult to isomerize alkanes at room temperature. And usually we have to heating up the system maybe above 200 degrees, 250, around that temperature. But by using this catalyst, we can isomerize alkanes at room temperature. Meaning this catalyst is very strong in terms of acidity. Okay, and another report by Jose et al. Here, they use also zirconia, but they add platinum here. And then after several calculations and reactions, Jose et al. Reported that in presence of hydrogen, they can enhance the activity of the catalyst and also the stability of the catalyst. Meaning in presence of hydrogens give effect some things on the reactions. So, and Jose et al. Reported make some conclusion that the role of hydrogen is to remove of coke hydrogenations. Meaning in presence of hydrogens, hydrogen can remove cokes from the space of the catalyst and can enhance stability and activity of the catalyst. This is the conclusion from Jose et al. And okay, and our proposal and our research group also focus on this area. I mean, we use also sulfate zirconia, and then we use also tungsten zirconia. Of course, we add the platinum, and we also use molybdenum zirconia, and we use some similar techniques to investigate the role of hydrogen here. And after several calculation and then using FTR, 2BD, and also XPS, so we made some conclusion that proton site is formed from our hydrogens, and this one is visible and dynamical. It means can be the amount of hydrogens can be set up. For example, if we were to just need a few months, we can set up it based on the temperature. Okay. Based on this reaction, we also extended to another catalyst for generalizations. We use also platinum silica added with SSF5, platinum aluminum, and also silica alumina, tungsten zirconia. So all of these catalysts give similar effects, give similar result when we put the hydrogen there. So we can generate Okay, this one is, for example, so the inclusion of the catalyst mean the effect of hydrogen here. If we do some reaction, we use carbon zirconia and we isomerize pentane to isoalkane. You can see here that in the presence of hydrogens, the activity we got about 0.5%, and when we change the carrier gas to nitrogens, we almost get nothing. Mean there's no activity there. Mean the presence of hydrogens mean not only remove the coke, but maybe do something to some reactions. Okay. In the other example here, we use sulfate combination between platinum and sulfate, platinum, sulfate, zirconia, and sulfate zirconia here. When we do the isolation of alkanes, pentane, so you can see here that in the early of the reactions, in the initial state of the reactions using sulfate zirconia, so we got the activity, but after a few minutes, after about 1 hour, the catalyst is deactivated completely. And but in presence of platinum, meaning we add platinum and catalyst, so we can keep the activity of the catalyst constant. Okay, then this one is the another example of communicating. So from the document from the we can get the product of benzene and propane here. So for the platinum sulfate zirconia, you can see here that in the presence of hydrogens, this one is the black one is the reaction at 470 degree Kelvin, and the white one is 427 Kelvin, 23 Kelvin. So you can see here that in the presence of hydrogen, so the activity is quite high. After we switch the carrier gas to helium, so the activity becomes decreased, and after we switch it again to hydrogen, the activity increases again. Means hydrogen plays a significant role in this reaction. Okay, after we from this reaction, so we can ask some question here, but hydrogen is not only to remove the coke, but hydrogen also do something to examine the reactions, maybe to activate, to increase the activity or something like that. So this is our question. And then so we also the function on the role of hydrogens on the catalyst using FTR. So we use SOP in FTR here, and you can see here when we increase the temperature in the presence of hydrogen, so you can see here okay, and we can see here in the left hand, you can see this picture. Please look at this thing and this thing and this thing and this thing. Change for this thing. So, okay, for heating in hydrogen, in the left side of the picture, so you can see that in the reactive side we decrease when we heat temperature, and protonic side increase when we increase the temperature. Okay, this one means because heat absorb on the surface area is just a proton pulse. When we change the amount of acidity on the surface, so heat will change from one reaction to another on the side. And from the right side of the picture, you can see that when we decrease hydrogen, so we can convert the process side to real acid side to exponential condition. You can see here in the left side A and the right side B is almost single peak. Meaning when after we decrease the real side, we convert the real acid side to process side, and then we put hydrogen, so we can get the original peak of the PV as of on the catalyst. Okay, this is more clear to understand. You can see here that triangle is reactive side and the circle is process side. When we think of the system in the presence of hydrogen, you can see here that this become decreased and process become increased. Means we can control the amount of protonic sites by changing the temperature. But then after we create the temperature, so means we create the source of proton. So you can see here that the protonic site will decrease and the site will increase. Means so you not exactly similar, but from the initial condition and the end condition quite similar. So we can change the amount of peroxide and use so reversibly, and we can set the amount of exercise using the change of temperature. Okay, this is the hydrogen deuterium experiments, because we are not sure, because when we absorb hydrogen at that, whether we can say proton or not. But by this result, we can make sure that hydrogens become protons and deuterium become E1. You can see here when we absorb hydrogen here, so when hydrogen does not dissociate with protons, we cannot get the peak of Sg. Mean after we absorb hydrogen and absorb deuterium, and both of hydrogen and deuterium dissociate to be hydrogen atom and deuterium atom, and next deuterium atom combines with hydrogen atom, and we get the peak of Sg. Mean on the surface of the catalyst, so there are dissociation process, mean from hydrogen to be protons and deuterium to be deuterium atom. This one is again with this result. You can see here that when we heating up the catalyst in the presence of hydrogens, you can see here that the protons, the PD will absorb all the new protons and use as set from the catalyst. Okay, and this is our experimental sequence. So you can see here, first we absorb hydrogen here, so hydrogen become protons, and after that we dissociate, we absorb deuterium, and then deuterium we get hydrogens, and after we dissolve all the material of the surface, you can get deuterium, hydrogens, and also has the combinations of S and D. So this one is clearly proof that hydrogens can be proton of the surface of the catalyst. Okay, this is our another result regarding the capacity of catalyst towards hydrogens, towards the generation of proton exercise. So you can see here when in the presence of in the absence of platinums, you can see here that almost no hydrogens generated, almost no proton generated from here. And then after we add platinum here, we can enhance the amount of hydrogen which is on the surface of the catalyst. Why means on the surface of the catalyst, platinum is required to generate proton. Okay, this is the just when we absorb at the different temperature. You can see here when we increase the temperature, the hydrogens will absorb on the catalyst will increase. This one is actually when we look at the absorption study. This one is exothermic reactions. When we this one is endothermic reactions. When we increase temperature, the amount of hydrogen will increase. Okay, this one is the proposed models of the generation of proton insights of this space of catalyst. You can see here that we have hydrogen here. Hydrogens will dissociate upon the platinums and become proton, hydrogen atoms, and after that, in the space of catalyst, so hydrogen become protons, and hydrogen release the electrons on the Lewis side. So you can look at here, Lewis set is also required here. If we don't have Lewis set here, we cannot generate proton. So with both of the Lewis and protons required to generate dynamics proton effect. This proton is not come from catalyst, but this one is come from hydrogen. Okay, this one is just another example of instrument cracking. So using copper-molten silica aluminum catalyst. So in the case of nitrogen and hydrogen, you can see this here. And if we put hydrogen, we got better result for nitrogen. So this one is platinum aluminum. Using aluminum for skeletal isomerization. You can see here when we use hydrogen, we got the result like this, and when we use nitrogen, almost we got the result. This one is PTC as I said. Okay, this one is the PNFR study for patterns of constant zirconia. This one is similar with patterns of zirconia. So you can see here This is the original video before we introduce hydrogen here. After we introduce hydrogen and heat it up at room temperature, the unit excitation increase and proton excitation increase. Means here we generate protons from the hydrogens. From this condition, we filtrate, we remove the hydrogen from the system. So you can see here that the process always will increase and the process will decrease. This one A and B will be quite similarly. Means from the original acidic water catalyst, so we can change the amount of the process by additional proton, by additional hydrogen and heating the system. Okay, this one we convert the bit to be more easy to understand here. So this one is exercise, this one is process exercise. When we heat the temperature, proton will increase, will decrease. And when we create the hydrogen from the space, so this one proton will decrease and proton will increase. Okay, this one is in the case of catalyst without platinum, so almost similar result here. And this one is our HD exchange experiment. You can see here that when we absorb hydrogen and deuterium here, so we also got HD here, means hydrogen is set to hydrogen atom, deuterium is set to deuterium atom, and then deuterium atoms and hydrogen atom combine. Some of deuterium atom and some of hydrogen atom combine become HD, and also hydrogen and also deuterium. This is the equilibrium failure of this reaction. You can see this temperature, for example, is 500 degrees here. So maybe around here, maybe this one is 150 degrees. If we do the experiment at 500 degrees Celsius, so we can get a value quite similar between platinum carbon zirconia and 3D and soft platinum carbon zirconia. And this one is for carbon zirconia. This one after we absorb 3D here. So we 3D and when we absorb the catalyst with 3D, so the acidity of the catalyst will become decreased. Mean because the inside was occupied by the 3D. So you can make sure that the 3D attack on the acid side, so the hydrogen and deuterium cannot dissociate and cannot generate acidity. Okay, this is the structure of the catalyst. It's not so important here. But this one is actually this one is the what we call it mechanism of the reaction. Participation of hydrogen here. Maybe from, for example, alkane to be alkenes and generate branching here, and then by beta fission, so you can get another product in tracking. You can get isobutane here, and you can also get propane here, and then our product is one. You can get isobutane. This is just the examples of the mechanism of the reactions. There are a lot of mechanisms there, so because depend on what we want to do. This one is for example. Okay, this one is as I explained before. This one. Okay, actually, what's the importance of molecular hydrogen oxygen proton excite? You can see here that when we do some reaction, the most important thing is the active site. So how we can adjust the active sites during the reaction? So because when we have catalyst and we use the catalyst, usually the catalyst is the mole of acidity is based on the structure of the catalyst. But we can adjust the acidity, the active site of the catalyst by using control hydrogen pressure of the temperature. When we increase the pressure of hydrogen, so we can increase the amount of proton, mean the amount of inside. When we increase the temperature, so we also can increase the amount of. So then for this one, so means we have to consider that hydrogens give big effects on the acidicalized reaction. Mean the presence of hydrogens and the presence of hydrogen will generate proton excitation, so we can take into account on the when we develop mechanism. So when we develop mechanism here, we have to consider about the protons which live from hydrogen. Okay, this one is molecular hydrogen oxygen. Now, this is my left idea hydrocarbon originated protonic acid site. Because when I do the reactions using anti-cathepsin product, in the absence of hydrogen, without any hydrogen here, so you can see here, this is the isomerization of the reaction. You can see here that we got also the selectivity of isomerization. So this is the conversion of reaction. This one is the selectivity. So when we use hydrogen, although the selectivity is selectivity, often the conversion is quite low, but because the selectivity is quite high here. So in the absence of hydrogen, actually we can also isomerize the alkanes here. This is another example here. So this is when we use ZXM5. So when we use the energy isomerization, you can see here that the conversions can be for 50% and selectivity around 10%. So it is quite high. We can consider that something generated during the reaction, because usually when in the absence of hydrogen, usually we cannot get this product. We cannot get any of isoprene. So okay, then after we consider that maybe during the reactions, protonic acid site which is required in the isomerization process maybe can be generated from the reacting agent. So we do some FCR experiment here. So this one is the heating of the catalyst in the presence of maybe this one is I think it's Alkane for injection. Okay, when heating up the system in the presence of hexane, so you can see here that this one is UAC side, this one is process side. When heating up, this one is UAC side, this one process side. When we heating up this catalyst in the presence of injection, you can see here that the proton start to generate. So means this one also, you can see the height of this, both of the beats. This is quite different, but this one will be quite similar. So this one convert to be here. After we create the head action here, so we can get the original of the catalyst. So you can see this one is quite similar. Okay. Based on this one, so we propose new concept. Hydrocarbon originated protonic site. From alkanes, we can generate this one. I'm not sure whether we have radical acting or not, but for sure we can generate proton hydrogen atom here, and hydrogen atom here spill over to the symmetrically, and then from here we get proton by releasing of electron to UAC side. In this case, we also need UAC side because to generate protons from atom, so we need something to trap the electron. So from the alkanes, so we can generate atom, hydrogen atom, and from hydrogen atom we can generate protons. This one is placed in the reactions of isomerization. So okay, this one is our new concept, but it's still in investigation because the last year I started this experiment because I got quite interesting result here, and then do some investigation using FER. This one is need about 1 year to set up all the system and to get this data. So then after that, this one is actually this one is what I'm doing now, because when we are doing catalysis and catalysis, this one is catalyzation, catalysis, and catalysis. This one is there's no techniques when you are playing with catalysis and catalysis. But we have here, we have not here, we don't have here. So that's here, you should not have this one to be catalysis. We can use a lot of technique here, thermal, catalysis, hydrolysis, chemical, soldier, etc. And we can do it very simple, and we have a lot of it. Okay, without the characterization of the product, so after the synthesis, so you can see we have all of this in Zoom. So you can do characterization. We are all of this and we are doing it. We have it, but we don't have it. Actually, you don't have here. But this one is the most important thing when you are playing with catalyst. You don't have here. Okay, now, design of reactor and product chemical tools. So this one is most important thing when you want to play with catalyst and catalysis. So now I try to solve this problem here. So one design of reactor. Now I will set up a reactor here. You can see here, this one can be used for, this one is for reactor reactor. So it can be used for gas reaction, vapor reaction, also liquid reactions. And this one can be used for high ambient pressure. This one is our overhead system. So this one is the typical results of that we are using this reactor. Usually this one is gas-phase reaction. So this one is DC, this one is the reactor. So this one is computer. So this one is online system. We can characterize the products in situ. We don't need to take out the products from the system. We just push the button so we can get this result. Okay, and then this one is in MTDC previously, but I don't know where now. President MTDC previously, but I don't know where is now. I don't know. So this one is in okay. After I set up this one, I set up another two. This one is FAKSA. This one is reactor, which can be used for very high pressure, high temperature. This one is quite robust. So and then the other ones I set up here in this one. So setting on the system, maybe next week or two next week we finish this one. This one coupled with GC. So this one is also a nice system, can be used for gas reaction, vapor reactions, also maybe liquid, but liquid maybe is quite difficult because we have to take out the products from the reactor and then manual injection in the GC. But it can be used for liquid reaction also. This one is like cheap, but this one is cost about more than 100,000. This one more than 100,000. Okay, and then FTR. Usually we are playing FTR, KBR, FTR. I mean just using KBR, I mean using for usual FTR. But I try to set up the high temperature FTR, which can be used for high temperature. And of course, this one can be used to absorb any probe molecules. So you can absorb here maybe alkanes, maybe 3D, maybe methanes, maybe ammonia, maybe whatever. So you can get this system. Yeah. And this is the typical our latest design. Here, I explained previously. This one is under IP application. This also under patent application. So and then this one is actually we have absorption apparatus to measure the sensitivity of catalyst, but that still is for physical absorption of material. So actually, when we are playing with catalyst, maybe this one is quite important. Absorptions are very. When we want to measure the probe molecular uptakes on the surface of the catalyst, so we can do this one. And this one is not finished yet. Maybe soon can finish it because this one needs vacuum system. So actually I'm waiting for the vacuum system which you see now. This one, okay. This one is maybe can be finished soon. And then the most important thing to operate this one and this one is this one, vacuum line. We should have vacuum line. Okay, actually we have two vacuum line. Vacuum line means what? Made by UV science. So, but this one is not finished yet. So, and previously they finished this vacuum line, but after they do some commissioning in the pressure of the system just hits -3 torr. I mean the order of the pressure is just -3 torr. So it's not so good. But after I set up this vacuum line, so you can see here that the order of the pressure changes with this system. It's quite good vacuum system, and this one is also finished. This one is finished, and this one is coupled with FDR and coupled with this one. Okay, then this vacuum line can be used for acid-base reaction. This is quite interesting because usually when you are playing with base reaction, you need high temperature, it means high vacuum. Otherwise, you almost cannot get any good product. So and then of course oxidation. So and then one we can do some exceptions on molecules or the catalyst. So and then one we can do some things also. So we can measure the protonic uptake by measuring the temperature change of the system. Okay, this is the next challenge. So I am planning to set up both of this one. One is hydrogen liquid exchange to because when we want to investigate the presence of hydrogen or protons, maybe this is the best technique to prove that we got proton or we got hydrogen or we got liquid. And the other thing is mass reactivity because this one is when we are measuring the distribution of active signs. So usually in our institutes we use just TDRO with TCD detector. But this one cannot distinguish between the moisture and also isotope from the water, also isotope from the ammonia. But when we use microwave TDR also, we can just choose the ammonia as the ammonia which does not affected by the presence of water. So this one is, I think it's quite expensive here. So because I think for myself it may be expensive, but mass is quite expensive. This one, both of these tools need mass detector. So I think it's quite expensive, but I think it's quite interesting to start here. Okay, and then this is our target. So my target this year, get 3,000 from IPC patents, also get 3,000 from patents. This is our target. So because I still have a grant, but that means I have to produce 3 patents at the IB. I have to produce 3 papers. This is the actual target behind this. Okay, that's all about my presentations. I would like to thank to Aisha, my previous supervisor for faculty, staff Lucia, and so staff at Cantina, and so all my students. Okay, thank you.